Okay, folks, let's go ahead and start. We are going to move now into the second model that we'll discuss this semester, and that is the overlapping generations model. So we finished talking about the solo model in great detail. And of course, one of the reasons why we did that is because some of the features of the solo model carry over to virtually everything we do the rest of the semester, particularly the features of the production function. Okay. All right. So what I want to do is spend the first part of today talking about just kind of the OLG model in general, the basic setup of the model, the inhabitants of the model, how they interact, so that you guys can get kind of a qualitative, descriptive, intuitive understanding of how it's set up differently than the solo model. It is more complicated in the sense that there's more going on. There is an actual consumer maximization problem at the heart of the OLG model that we'll have to work with. But before we get into any of that math, I want to talk about some of the basics and some of the motivation for why we even want to study the OLG model. So the overlapping generations model was first developed by Samuelson in 1958 and also Diamond. They have two classic papers. The Diamond paper is 1965. Those should be available on Blackboard if you want to take a look at those. It is the first model that we're going to study in this class where aggregate demand can be built up from a coherent microeconomic story, right? In the solo model, we made this assumption about aggregate demand, that it was based on an assumption about households basically saving a constant fraction of their income every period. In this model, we're going to derive the savings decision optimally from coherent microeconomic foundations. The name of the overlapping generations model is almost self-explanatory. The name implies the structure. Okay, at any one time in this model, you're going to have people who belong to different generations who are alive and who may be interacting or trading with one another. And so you've got generations, different generations, trading with each other at different points in their lives. Another important feature of this model is that there are actually generations who are yet unborn. So future generations whose preferences are not taken into account in current transactions. However, those transactions, if they affect the capital stock, which evolves over time, will affect the market prices that future generations face. All right, that's one of the key features of this model that actually gives rise to a particular type of externality, which implies some interesting features of this model relative to some of the others that we're going to talk about later on in the semester. The OLG model is used widely in the study of macroeconomics primarily because it makes it possible to study the aggregate implications of what's called life cycle saving. Okay, so the life cycle model, this idea that individuals save when they're young while they're working so that they can finance their consumption expenditures when they are retired and not working, has implications for the capital stock, right? Because the primary vehicle with which people save in this model is going to be purchasing capital. That's the durable good that's going to generate a return to your savings later on. And so this whole idea of life cycle savings, to save some of your income when you're young, to finance your future consumption, we can examine or analyze the aggregate implications of that type of life cycle behavior in this model. You can't really do it in the other classes of models that we're going to study later on in the semester. It's a useful model because it also allows us to study the effects of how government policies might interact with life cycle savings. Can certain taxes or transfer programs impact your decision about how much you want to save, right? We'll study some of that before we leave this model as well. So given all of that, you know, all of that might be enough to justify studying the overlapping generations model all on its own. But there's a number of other reasons why I think the OLG model is important. It's one of the 3 or 4 main workhorse models that you will see in modern macroeconomics. Let me just kind of briefly talk about a few of these other reasons. It's really one of the only models, if not the only model, that captures the interaction of different generations that are engaging in trade with one another in the marketplace. All of the other models that we're going to talk about don't capture that behavior at all, that you could have potentially young people trading with older people. 2, it provides a very tractable alternative to, I think, what has undoubtedly become the most popular model in macroeconomics, and that's this infinite horizon representative agent model. In the overlapping generations model, people are born, they age, and then they die. And every period, new people are born. And every period, some people die. In the most common dynamic macroeconomic model, agents are assumed to live forever. That is, they have an infinite horizon, but they discount the future at a constant rate. The OLG model is one of the few very tractable models that provides a useful alternative to that representative agent model that we're going to start talking about in a few weeks. Some of the key implications of the OLG model are different from the neoclassical infinite horizon growth model. I think probably the most important is this idea that in the OLG model, Adam Smith's invisible hand principle doesn't necessarily apply, in the sense that if all agents are behaving optimally to maximize their own lifetime utility, you could end up with a situation where the outcomes that emerge in a competitive, kind of decentralized environment are not the same allocations that would be chosen by a so-called benevolent central planner. Those allocations may not even be actually Pareto optimal, right? This idea where you can move allocations around in a way that makes at least one person, one agent better off without making anyone else worse off. And this whole inefficiency in the OLG model stems from this problem, or this externality, where decisions that are made in the present are going to affect the prices that unborn generations face in the future. It's what's called a pecuniary externality. We'll get into the details about this in the next few days, but what you're going to find out is that generates a tendency for people in this model, for the inhabitants of the model, to actually save too much relative to what a benevolent central planner would choose. And so the capital stock in the OLG model can actually over accumulate beyond the golden rule level of capital, for instance, that we talked about in the solo model. So one of the interesting features of analyzing fiscal policy, tax and transfer programs in the OLG model is that it turns out a well-designed fiscal policy can sometimes unwind those distortions and help the OLG model come back closer to what would be dynamically efficient, right? But left on its own, the OLG model very well could converge to a dynamically inefficient steady state, where individuals are actually saving too much and consumption in the long run is therefore too small. That's one of the really interesting implications of this model, is that it provides a really tractable illustration of a model where that invisible hand principle fails, right? Which is goes back to the fundamental welfare theorem of microeconomics, right? Have you guys heard about that? Talked about it in micro yet? It's this idea that if agents are behaving optimally in a frictionless world, there are no distortions, there are no asymmetries of information, that it's a purely distortionless world, then the competitive outcomes, that is what we choose in order to maximize our own well-being, would be the same allocations or outcomes that a benevolent central planner or social planner would choose. That situation emerges in the neoclassical infinite horizon growth model, because there are no frictions there, no distortions. But in the OLG model, the existence of these externalities, due to the fact that there are people who aren't born yet, whose preferences matter to a social planner, but who don't really matter to people who are alive and trading with each other today, that can give rise to these dynamic inefficiencies. And we'll spend some time illustrating exactly how that happens and how severe those problems can be. Okay, I know that's a lot to soak in before we even get down to the nuts and bolts of the model, but that's really what this whole model is really all about. Now, there are many complicated forms of the OLG model that you can find in the literature. We're going to work with the most simplest version, in which people are assumed to be born, they live for exactly 2 periods, and then at the end of that second period, they die. So they're young in the first period of their life, they're old or retired in the second period of their life, and then they expire. So you can think of a period in this OLG model as not being a quarter or even a year, but several years, if not decades, where you have the kind of the working phase of your life and then the retirement phase. All right, that's the time frame we want to work with here. And we want to keep the model as simple as possible to work with just 2 periods. When we talk about the infinite horizon optimal growth model, it's going to be obviously an infinite number of future periods. Here, we're going to look at our dynamic model is just going to be a 2-period problem that we need to analyze. And it keeps all of the math as tractable as possible. Nevertheless, we can still derive some interesting implications about how individuals' endogenous savings and consumption behavior impacts the evolution of the aggregate stock of capital. This is, at the end, a growth model after all, right? So keep that in the front of your minds. This is just a growth model that is built up from coherent micro foundations. Ultimately, what we want to do here is figure out how the capital stock evolves in this environment. And it would be useful for you to compare and contrast that evolution with what we saw in the solo model. That's going to help you understand it a little bit better. We just need to build up that story of how the capital stock evolves from an actual microeconomic story. Okay? Y'all have any questions then before we get started on the specifics here? No? All right. Let me, I have this as labeled, I guess, chapter 2 in my notes, so I'll keep that consistent. We're going to do the baseline OLG model. And the first thing we're going to talk about, you should already know this, is that we need to talk about the specifics. That is the demographics, preferences, and technologies that characterize this new world. All these different models we talk about are storytelling models, okay? Each of them tell a story. You have to understand the agents who are inhabiting them and how they interact, their rules for behavior, etc. All right, and that's how we're going to set this up here in the first part. So each individual in the OLG in this 2-period OLG model lives, of course, for exactly 2 periods. So an individual that is born at the beginning of date t is going to be alive and working and saving in date t, and then will be consuming out of his or her savings at date t plus 1, and at the end of date t plus 1, that person will die, okay? And a whole new generation of people is born at the beginning of every single period. So it's just a 2-period problem. Now, each individual that is born, let's say at date t, is going to have the following utility function defined over their lifetime consumption. So let me be very clear about this notation. So their utility depends on their first period consumption, C1t, and their second period consumption, C2t plus 1. Now, what does C1t reference? The 1 in the subscript indicates that we're talking about a young person. The T indicates what period we're talking about. So C1T is the consumption of a young individual who was born at the beginning of date T. That young individual becomes old at date T plus 1. So C2T plus 1 is the consumption of an old person at date T plus 1, who was obviously born in date T. So that's what the utility, and so the utility function is going to be what we call separable over time. So it's going to depend on first period consumption plus the discounted utility value of second period consumption. So it's these period utility functions which matter for us. So a person's lifetime utility is just the discounted sum of their utilities for every period of their life. Beta is the discount factor. So this is a number somewhere between 0 and 1. Right now, in a model that is calibrated to a quarterly frequency, usually beta is something like 0.99. But for a model that is calibrated to several decades, beta is going to be much smaller than that, closer to 0, right? But we're just going to treat it as the discount factor. We're not going to assign a particular number to it yet. Okay. Assumption 1. A lot of the features of the OLG model carry over from the solo model, particularly with regards to the production function. What is new is obviously the utility function. So we need to talk about that for a minute. This utility function, U of C, is defined on the positive reals. It's going to be strictly increasing, concave, and twice differentiable. Okay, so the first derivative of utility is positive. The second derivative we're going to assume is negative. That captures the idea of diminishing returns to consumption. Greater consumption gives you greater utility, but at a diminishing rate. And this is true for all C in the interior of its domain. So all positive values of C. That's the only assumption you need to recall for the OLG model. So utility is continuous, differentiable, first derivative is positive, second derivative is negative. Okay, individuals can only work in the first period of their lives. And they do so by supplying 1 unit of labor inelastically. All right, so in this model, there is not an endogenous labor-leisure decision. Utility only depends on consumption. It does not depend on how much leisure you consume. So every period, every member of this young generation is simply going to supply 1 unit of their labor inelastically, just like we saw in the solo growth model. Okay, and they're going to receive a wage payment in exchange for that 1 unit of labor. So WT is the real wage that is given for 1 unit of inelastic labor. We're going to assume that there is also growth in the population, and it is exponential, just like the solo model. So the number of young people, LT, that are born into the world at date T is just equal to 1 plus N times the number of people who were born in the last period. In other words, it's 1 plus n raised to the t times the initial endowment of people in this world. So there is exponential population growth, just like we saw in the Solow model, where the population grows at rate n. Okay? Stop me if any of you all want to talk about any of this in any more detail here. How about the production side of the economy? It's basically the same as the Solow model. We're going to assume here that there's a continuum of perfectly competitive firms that produce a common finished good, and therefore we can represent aggregate supply using a aggregate production function. All right, so the amount of finished goods in the economy, output, which is also equal to income, Y, is a function of the economy's stock of capital, aggregate capital, KT. It's a function of how many workers there are in the economy, LT, that's the number of young people in the economy, and it's also a function of the state of technology. This production function F is neoclassical, so it satisfies all the assumptions we talked about earlier. It has positive returns to labor and capital, the second derivatives are negative, and it satisfies the Anata conditions, right? So it's a neoclassical production function. Now let me make a quick comment about this. In the Solow model, how do we interpret LT? That was just the population. Everybody works 1 unit of labor inelastically. Be careful. In the OLG model, LT is not the population. This is just the number of young individuals in the economy. What is the population at date t equal to? It's the number of young people born in date t, but it's also added to that the number of old people who were born in the last period. So the total population in date t is actually LT plus LT minus 1. However, the only people who are working in any given period are the young. So LT here is not population, it's just the number of young individuals. So that's going to possibly create a little confusion for you, because one of the things we did to the Solow model, which we're going to do to the OLG model, is transform all of the variables into their intensive form. That is their per capita representations. There's a difference in the OLG model between per capita variables and per worker variables, right? Because the whole population is LT plus LT minus 1. The normalization that we're going to do is to divide by LT. So the lowercase letters that we're going to work with that are stationary in this model are per worker variables, but that's not necessarily the same thing as per capita. Okay, just keep that in mind. Okay, factor markets are perfectly competitive. So capital and labor are traded in competitive markets, and the implication of that is going to be that the real rental payment to capital, which I'm going to call RT, is just equal to the marginal product of capital. Now, be careful about this. The actual returns to capital, which I'm going to call lowercase r, that should be equal then to the real rental payment that an owner of capital receives, but capital we know depreciates. So the real return to capital is big R minus delta. Okay, and so the marginal product of capital here is equal to the real return to capital plus the depreciation rate. All of that follows from cost minimization or profit maximization of competitive firms. What should the real wage be equal to? That should just be equal to the marginal product of labor, right? F sub L, KT, LT, AT. So these two equations held in the Solow model are also going to hold in the overlapping generations model. All right. It's going to prove useful for us again to work with variables that are in intensive form. These are the variables that will be stationary in a steady state if one exists. Okay. So when working with one of these models, the first thing you want to do is transform the variables. We are going to work with per worker variables, not per capita. So we're going to define our lowercase k in this model is aggregate capital divided by the current workforce, LT. Output per worker is an economy's total output divided by the number of workers, not by the whole population. Now, if we make an assumption here that technology is constant for all t, so we're going to carry that assumption over from the Solo model, then we can do our transformations in exactly the same way, right? What is output per worker going to be equal to? It's F of little k, 1 and A, which we can simply write as little f of little k, right? So output per worker is just a function of capital per worker. The real rental payment, which is the real return to capital plus depreciation, is just equal to the marginal product of capital, which we know in intensive form is just the slope of the per worker production function. That follows from constant returns to scale and Euler's theorem. And what's the real wage equal to? We can also write the real wage as a function of capital per worker. Hopefully you recall that it's F of k minus k times F prime of k. These three equations follow from constant returns to scale and Euler's theorem. All of that carries over from the Solo model. Okay, questions so far? I can't stress enough how important it is for you to be able to kind of talk your way through the model. All right. I always found it very helpful, not even to write anything down, but just to actually explain in words what's going on in the model. All right. Who inhabits the model? What are their demographics look like? What do their preferences look like? You know, how long do they live? Who do they interact with? If you can tell yourself that story, I think the math follows from that pretty naturally. Okay, let's talk about the consumption and savings decision then of individuals in this economy. What we're going to do is we're going to actually work through the consumption, the savings decision of a representative type of individual that is born into this world at date T, right? Everyone has the same type of preferences. Everyone has the same type of job and faces the same income constraints. And so everyone who's born at date T is going to make the same decision. This model only has heterogeneity in it because we've got people of different generations interacting with one another. But everyone who belongs to the same generation is homogeneous. They behave exactly in the same way. Okay? So let's look at the savings and consumption decision then of a young individual who is born at the beginning of date T. We can describe their behavior through a simple constrained optimization problem. What this person wants to do, let's think about this, is to maximize their lifetime utility, right? That's your goal. If you're born at date T, you know you have some preferences and you know you're going to have some income by working. What you want to do is try to maximize your lifetime utility. Well, what is your lifetime utility? It's the utility over your first period consumption plus the discounted utility you get over your second period consumption. There are three variables that you are maximizing over. One is your first period consumption. The other is your second period consumption. But the other endogenous choice variable here is also the amount of savings that you want to engage in the first period of your life, which I'm going to call ST. So your lifetime consumption, C1 and C2, as well as your savings decision when you're young. Now, how is a person who's born at date T, their consumption, how is their consumption or lifetime utility problem constrained? This is not an unconstrained problem, it's a constrained one. This person is going to have income constraints that they face in both periods of their life, all right? Well, what does that income constraint look like when they're young? Well, quite easy. Their consumption plus whatever they decide to set aside in the form of savings has to be bounded from above by their real wage. A person is not born into this world with any resources other than her labor, all right? And she's going to work one unit of labor inelastically when young. So your total consumption plus your savings in the first period must be equal to or less than or equal to your real wage. Now, how is your second period income constrained then? Now think about this. You should be able to write this down really just by telling the story about what's going on. In the second period, people don't work, right? They're retired. And their consumption is financed with what they saved from the first period of their life. So C2T plus 1 is going to be equal to what? Whatever their first period savings is times a gross interest rate, right? Well, what's the only way we can save in this model? By investing in the capital stock. So the amount of consumption when old is going to be how much you decided to save when young times 1 plus the return to savings in period T plus 1. Now let me make sure you guys have the timing of all this down right before we actually work through the math, which is not hard to do. Here's how things work. So at the beginning of date T, you have everyone who is young is born, okay? Those individuals go to the labor market and they supply a unit of their labor inelastically. Production occurs then in the economy, and those young individuals receive a wage of W, all right? Now, during that period, while you guys are working and I'm retired, I own capital, that is savings that I accumulated from the last period. I'm going to rent my capital to firms. Firms are going to take that capital and take your labor and combine it to produce output, okay? So firms are then going to pay me a rental rate and they're going to pay you guys a real wage. Now, before you decide to eat, before you decide to consume, you need to make a savings decision, right? And so part of your wage is going to be devoted towards savings. And in this economy, the only vehicle that you can save in is through the capital stock. And so what you're going to do is you're going to purchase the capital stock from the old generation directly from me. I'm going to give you all of my capital in exchange for those resources. At that point, you then eat whatever's left over, and I'm going to consume my savings plus whatever return I got on that savings when I rented my capital stock to firms. So consumption occurs in this model within each period after all of these financial market transactions have taken place, right? So savings and factor payments, all of that take place before people actually consume goods and services. Once you guys consume, and once I consume, I drop dead. You guys become old, and then in the next period, you rent your savings, your capital stock to firms, and the process starts all over again. Okay, that's the timing of this, of how this model works. So consumption kind of occurs at the very end of every period, after these financial market transactions have all occurred. Okay. Any questions about that? Pretty straightforward. All right, so there's, of course, several ways to solve this. One way is you could set up a Lagrangian, right, with two constraints. I don't want to do that. What I'm going to do is I'm going to actually simplify this down to a one-dimensional problem where I'm maximizing just over savings by substituting the constraints into the lifetime utility function. So I'm going to rewrite this as the max over ST of U of C1. Now, what is C1? C1 is WT minus ST. By the way, we know both of these constraints are going to bind. Why? Because utility is strictly increasing in consumption, right? We're not going to have, after we've made our savings decision, whatever's left of our wage, we're going to consume. There's not going to be any left over after that, right? So so the constraints themselves will bind in equilibrium. Plus beta U of C2T plus 1. Well, what's C2T plus 1? That is 1 plus RT plus 1 times ST. So I've transformed this into a maximization problem then, where we're just choosing our optimal level of savings. One other thing I should mention, or two other things really. You'll notice that in neither of these constraints do we have a bequest motive or an altruism motive, right? You guys don't care about your offspring. What you want to do is you want to consume in the second period of your life all of your resources. You don't want to take into the grave any unused savings, and you don't want to bequeath any of those resources to your children. There's no bequest motive here. The other thing, there's no borrowing in this model either, and in the sense that ST has to be greater than or equal to 0. Now, we actually don't have to impose this constraint on the problem, and why is that? Because think about it. Let's suppose we borrowed in the first period of our life by choosing a negative level of savings. Then what does that imply about period 2 consumption? It would have to be negative, right? A negative number times 1 plus R would be negative. And we can't have negative consumption in this model. It violates the assumption about the utility function. So there's no borrowing going on, but we don't actually have to impose this as a constraint on the problem. It's just going to be, it's going to turn out that S will be strictly positive. Okay? So let's do the first order condition then. It's pretty straightforward. S appears here and here. So let's see, it's going to be a negative U prime of W minus S, which is just C1T, plus beta times, let's see, there's a 1 plus R attached to this S, so you got to use the chain rule. So it'll be beta times 1 plus RT plus 1 times U prime of C2 T plus 1. First order condition has U prime of C1 times negative 1 plus the discounted value of next period's marginal utility consumption, the sum of those two being 0. This is what's called the consumption Euler equation that takes a slightly different type of form in the infinite horizon version of the model, but is very much related to this. It shows how essentially the real interest rate, as well as the time rate of preference, that is the discount rate, is going to be related to the growth rate of consumption over time. We'll talk more about this a little bit later. But this thing is called the consumption Euler equation. Not to be confused with Euler's theorem. Okay, we need to verify that we're in fact dealing with a maximization problem rather than a minimization one. So what does the second order condition look like? You have to take the derivative of the first order condition again with respect to S, right? So So it's, let's see, C1 is W minus S. So you're going to have another negative there in your chain rule argument. So it'd be U double prime of C1t plus beta times 1 plus R t plus 1 squared U double prime of C2 t plus 1. What's the sign then of the second order condition? What's the sign of U double prime? Negative plus beta times 1 plus R squared. That's a positive, but U double prime is negative, so it's a negative plus a negative, so the whole thing is less than 0. So the savings level that satisfies the first order condition is the one that maximizes lifetime utility, not minimizes it. All right, now let's go back to the first order condition. What it says is that the marginal utility of consumption in the first period of your life, so U prime of WT minus ST, has to be equal to the discounted value of 1 plus RT plus 1 times the marginal utility of second period consumption. This first order condition must hold for an open set of values around ST, WT, and RT plus 1. What are the variables that are time varying in the Euler equation here? WT, RT plus 1, and ST. And so that Euler equation, because the utility function is continuous, should hold for an open set around the values of S, W, and R. Well, that's awesome, right? Because by the implicit function theorem, then, we know that ST can be written as a function, then, of the two factor payments, WT and RT plus 1. And that the first order condition, then, can be rewritten as U prime of WT minus S of WT RT plus 1 is equal to beta 1 plus RT plus 1 U prime 1 plus RT plus 1 times S, which again is a function of WT and RT plus 1. That's going to be useful for us. Why is that? Because if we know that the optimal savings decision is some implicit function of the factor payments, we can then determine explicitly how one's savings decision is going to be affected by marginal changes in the real wage and the real return to capital. Now, in the solo model, savings was exogenous and constant, right? In the OLG model, however, the real wage and the real return to capital are going to evolve over time as the capital stock accumulates. Remember these two equations. Or maybe I should show them down here. As capital per worker accumulates over time, the wage and the real return to capital will evolve. As those factor payments evolve, that's going to cause people's savings choice to evolve as well. The key question we have to eventually answer is whether or not the model will settle down to a steady state level of capital, at which point the level of savings will also be fixed. Okay, any questions so far? Now, I told you at the beginning, really the main thing here is to keep in mind that this is indeed a growth model. And so what we want to do is we want to build up this story about how the aggregate stock of capital evolves over time from these coherent micro foundations, that is people's optimal savings decisions. And what we want to do is derive a fundamental law of motion from the OLG model. How different is that going to look than the one in the solo model? Okay, so where do we start here? Let's see, law of motion for capital. The economy is closed and there is no government sector, just like in the solo growth model. So a nation's income or total expenditures then are going to be allocated between aggregate consumption and aggregate investment. That is the same as before. And so this means that investment is just equal to income minus consumption, which of course is the same as national savings. So that's a big S, not individual savings from the last slide. So just be mindful of that. Now, how does the capital stock evolve? The capital stock evolves in the exact same way, really, as it does in the solo model, right? The evolution of the capital stock is really an identity. It says that the change in capital from one period to the next, from t to t plus 1, should be equal to what? It should be equal to the amount of new investment that is undertaken in period t. That's the force that tends to lift the capital stock, minus depreciation. This is a more or less an accounting identity that must hold in all of the models that we're talking about. Now, there are some macro models that assume that there are adjustment costs of capital or adjustment costs of investment, and this equation changes somewhat. But in the models that we're looking at, we're going to assume that they're free of those kinds of adjustment costs. And so capital only grows between t and t plus 1 if a country's investment exceed its depreciation, right? Okay, well, let's plug in what we know about I. Investment is what? Is the nation's income minus its total consumption. Here's where we can start looking at some of the implications then of the OLG model. What does this nation's income look like? Well, it would be the total payment to labor. So that's the real wage times the number of people who are working, which would be what? LT. Plus the total payment to owners of capital, which is the real rental payment, capital R, times the capital stock. Well, what is the real rental payment equal to? It's the real return to capital, little r, plus depreciation times the aggregate stock of capital. Remember, this follows basically from Euler's theorem. An economy's total output should be equal to the real wage times the marginal product of labor plus the real rental rate times the marginal product of capital, right? So, I'm sorry, let me back that up. An economy's total output is the marginal product of labor, that is the real wage, times the number of units of labor, plus the marginal product of capital, that's the real rental rate, times the number of units of capital. That follows directly from Euler's theorem. So this here is equal to YT. Now, what does aggregate consumption look like? Well, you've got the consumption of two different types of individuals, right? You've got young people, C1T, and you've got LT of them. But you've also got the consumption of current old people. So not C2T plus 1, but C2T, right? Now, how many of those old folks are there in period T? LT minus 1. So aggregate consumption is C1T times LT plus C2T times LT minus 1. And then we have minus depreciation. All right, some of this already cancels. We've got a positive delta KT and a minus delta KT. Now, what is W equal to in the OLG model? That is from the budget constraint, C1T plus ST times LT plus RT KT minus C1T LT minus C2. Well, what is C2T? From the budget constraint, that is actually 1 plus RT times ST minus 1, correct? C2T is 1 plus RT times ST minus 1. It's the total gross savings then, plus the returns to capital of the current old generation. So we have the change in the capital stock then is equal to this. A few more things cancel. C1LT minus C1LT, that's gone. And let me swing this capital over to the right-hand side. So KT plus 1 would just be equal to ST/LT plus, let's see, 1 plus RT times KT minus ST minus 1, LT minus 1. And again, what we're trying to do here is derive the fundamental law of motion for the capital stock. All right. How can we simplify this more? Remember when I told you a few minutes ago that there's no bequest motive in this model? Let's assume that K1 is the initial capital endowment of the initial size of the old population when the world begins in this model, right? So at time t is equal to 1, in the very first period of this model, there's got to be some amount of old individuals that have collectively capital stock K1. What is going to be the consumption of that initial old generation? Well, let's see, that's C2, 0, right? So that would be the consumption of an old generation. I'm sorry, not C2, 0, C2, 1. That's the consumption of an old individual in the first period of this world, right? Times the number of those types of individuals. That's going to be L0. Right, L1 is the number of new people born in date 1. So the number of old people who are endowed to the world at date 1 would be L0. Their total consumption, because there's no bequest motive, should be equal to 1 plus R1 times K1. Right? Can we use this information then to simplify the equation that's right before this? Well, what would K2 minus K1 be equal to? If we go back up to that line, K2 minus K1 is, let's see, W1 L1 plus R1 K1 minus C1 1 L1 minus C2 1 L0. So K2 is, let's see, what is W1? That is, no, I'm sorry, let me group the L1 terms. So that's W1 minus C1, 1, all of that times L1, plus, if I bring this K1 to the right-hand side, it's a 1 plus R1 times K1. And then the only other thing I have to account for is this minus C21 L0. Well, if there's no bequest motive, then C21 L0 is equal to 1 plus R1 K1, right? So that and that cancel. And you're left with K2 is equal to W1 minus C11. Well, that's just S1 times L1. So the capital stock in period 2 is just the total amount of savings that takes place in period 1. Well, let's do this one more time. What would the capital stock in period 3 be equal to then? And for this one, let's appeal to this equation. K3 is just what? S2L2 plus 1 plus R2 times K2 minus S1L1. Well, K2 is equal to S1L1. So that goes to 0, which implies then that K3 is equal to S2L2. You guys see the pattern? K2 is equal to S1L1. K3 is equal to S2L2. You can best be sure that K4 is going to be equal to S3L3. So if we were to do this many, many periods, by induction, we could prove that KT plus 1 is just going to be equal to ST times LT. In other words, and this should be intuitive, the aggregate stock of capital that we carry into period T plus 1 in the OLG model is just the total amount of savings that the young generation conduct in period T. So ST is the per worker savings, LT is the number of workers. Well, that's helpful. Why? Because we know endogenously how ST is determined. ST is a function of the real wage and the return to capital at date T plus 1. So that optimal savings function times the number of young individuals is what determines then the capital stock at date T plus 1.
So to make sure I'm following correctly, when you're referring to S for savings, this is the aggregate and not the
ST is the individual savings decision of a person who's born at date T.
Okay.
The total aggregate level of savings would be your individual savings plus the number of people in your cohort. That's LT.
Okay.
So savings times the total number of workers is aggregate savings in the entire economy. And that determines what the capital stock is going to be in the next period.
Okay.
Because capital is the only vehicle that we have to save in this model. Okay, let me define what an equilibrium is then. I think I can do that before we conclude for today. What is an equilibrium then in the canonical two-period OLG model? Now let me stress, this is not just any equilibrium, it is a competitive equilibrium, right? Here, we don't have a central planner that's determining allocations. We have individuals behaving optimally. And by the way, they're determining their level of savings and their consumption levels by taking as given. I didn't really emphasize this, but when you are Richard, right? When you're determining your consumption and savings decision, notice what you treated as exogenous in your own maximization problem. The factor payments, you took that as given, right? You didn't, in other words, you didn't think about how your own savings decision is ultimately going to impact the wage or the rental rate. You treated that as exogenous or given from the perspective of your optimization problem. Firms also take the factor payments as given. But in equilibrium, labor supply is equal to labor demand, capital supply is equal to capital demand. And we know that market's clear because the factor payments will adjust in equilibrium. So W and R are endogenous variables in equilibrium, but they're exogenous from the perspective of an individual consumer who's maximizing her lifetime utility. A competitive equilibrium is a sequence of, in this, and I'm going to define this in terms of a stationary competitive equilibrium. So the variables that I'm characterizing in my equilibrium process here are the ones that are stationary, not the aggregate variables, but the per worker variables. So a stationary competitive equilibrium are sequences: capital per worker, consumption of a young individual, the consumption of an old individual, the savings of a young individual, the return to capital, as well as the real wage. So it is a sequence of objects, 1, 2, 3, 4, 5, 6 of these things, from some initial date to infinity, that have to satisfy the following conditions. Well, the first two conditions are the conditions that characterize the optimal behavior of firms. Firms are maximizing profits, taking the factor payments as given. And so what describes optimal firm behavior in this model? It's that the real return to capital is equal to the marginal product of capital minus depreciation. And that the real wage is equal to the marginal product of labor, F minus K times F prime. These first two equations describe the optimal behavior of firms in the OLG model and really characterize the evolution of R and W. Now, what is it that characterizes the optimal behavior of C1, C2, and S? These are the endogenous outcomes of the consumer optimization problem, right? Well, the most obvious one, of course, is the Euler equation. U prime of C1 was equal to beta 1 plus RT plus 1 times U prime of C2 T plus 1. The consumption Euler equation determines your optimal savings decision, ST. And once you have your savings decision, you know what C1 and C2 are. They can be determined from the budget constraints. C1T plus ST is equal to WT. C2T plus 1 is equal to 1 plus RT plus 1 times ST. We have how many equations then in our equilibrium? 1, 2, 3, 4, 5. And how many objects are we trying to define in this stationary competitive equilibrium? 1, 2, 3, 4, 5, 6. We're missing one equation, right? And what equation are we missing? It's the key aggregate market clearing equation in this model. It's the law of motion for the capital stock. However, we've written that law of motion here in terms of aggregate capital. What does it look like in its intensive form? Well, you guys can do that. In intensive form, it's capital per worker times 1 plus N is going to be equal to ST. If we just divide both sides of that law of motion for capital by LT, you get little k t plus 1 times 1 plus N is equal to savings per worker. which we know is going to end up being a function of the real wage and the real interest rate, or the real return to capital. We need an initial condition, right? The economy is endowed with some initial level of capital per worker. That's given. So given initial capital per worker, these 6 equations then fully characterize the stationary competitive equilibrium in the OLG model. Once if you're given K0, you should be able to figure out K1, C11, C21, S1, R1, W1, all of the time 2 variables, all of the time 3 variables, and so on and so on and so forth. Again, notice that this notion of an equilibrium is a dynamic concept. It's not a static concept. I believe in the notes I might have not characterized this as a stationary competitive equilibrium. I might have left aggregate variables in there, but I think it's probably more useful. You can technically do that, but it's probably more useful when you're trying to solve the model analytically to go ahead and write this thing as a stationary competitive equilibrium. So that means transforming the relevant aggregate variables like the capital stock into their per worker forms. Now, by the way, we could also add another variable here, right? What if I wanted to characterize my equilibrium also over values of output per worker? Then I would need to add another equation to my equilibrium statement, right? And what would that be? Output per worker is equal to what? F of KT, right? So here I've got 1, 2, 3, 4, 5, 6, 7 objects and 7 equations. Or alternatively, you can simplify it. You can perhaps take R and W out of the equations by substituting them into elsewhere, right? And write it only as a function of C's and S's and K's. The thing you need to remember, I don't really care how large or compact your definition of an equilibrium is. You just need to have the same number of objects you're solving for as you have equations. It needs to be identified. Okay, I just have a couple of minutes left. Let's preview what we're going to do in the next class. So we've set up the model. We've characterized the equilibrium, right? What is the next thing we want to do? What do we do in the solo model after we characterize the equilibrium and the fundamental law of motion? We try to think about whether or not the model exhibit a unique, stable, steady state. Okay, that's the next step of this process. What does the OLG model imply about the existence or lack thereof of a steady state? Well, if a steady state level of capital exists, then it must satisfy the law of motion for capital in this model, which is capital per worker times 1 plus n is equal to S. Well, what do we know S is? S is a function of the real wage, WT, and the real return to capital at date T plus 1. Remember, that was what we found in our consumption Euler equation. Well, what's the functional form of the real wage? It's just F of KT minus KT F prime of KT. And what is the functional form of RT plus 1? It's F prime of KT plus 1. Be careful about your time subscripts here, minus delta. This is what the fundamental law of motion looks like in the OLG model. Now, read that very carefully. It says that KT plus 1 times 1 plus n is equal to S of 2 arguments. F of k minus k times F prime, and F prime of KT plus 1 minus delta. Do you guys see any challenges or difficulties there in trying to solve for KT plus 1? In the solo model, we could actually solve for KT plus 1 as an explicit function of KT. We could derive this nice, easy mapping between KT and KT plus 1. Well, what do you see in this equation? I see a KT plus 1 on both sides of this equation. Unfortunately, On the right-hand side, that kt plus 1 is a function of f, which we haven't defined explicitly, which is also in turn a function of s, which we haven't defined explicitly. S will depend on the parameters of the utility function. So we cannot solve explicitly for a law of motion for capital in this model. And so this mapping between kt and kt plus 1 is not necessarily going to behave as nicely as it did in the Solow model, where we had this nice monotonic convergent dynamics, right? Where the mapping crosses the 45-degree line only once at a slope of less than 1. This equation is not restricted enough in order for us to prove that a unique steady state exists, right? If a steady state exists, what equation must it satisfy? K star times 1 plus n is equal to S of, let's see, F of K star minus K star F prime of K star. That's already getting ugly, comma F prime of K star minus delta. Unfortunately, this equation, without further restrictions on the production function and on the utility function, does not necessarily admit a unique stable equilibrium. What we're going to do in the next class is we're going to talk about another set of restrictions that we've got to impose on the model. In particular, we're going to use a Cobb-Douglas production function on F, and we're going to use a particular class of utility functions called constant relative risk aversion. It's basically a power utility function, okay, which is going to help us determine what S is going to look like. If we're willing to make those restrictions or assumptions about utility and the production function, then it turns out that we can prove the existence, uniqueness, and stability of the steady state in the OLG model. But absent those additional restrictions, we can't actually even prove that a unique steady state exists. That's what we're going to do in the next class, is I'm going to show you a basic argument where we could have actually multiple steady states in this model. And then we're going to look at a couple of parametric restrictions on utility and production that allow us to generate a unique, stable, steady state in the OLG model. And in fact, if we go one step further and assume that utility is logarithmic, not just CRRA, but that utility is the log of consumption, then it turns out that the OLG model, the two-period OLG model, collapses to something that is basically indistinguishable from the Solow growth model. And we'll talk about the intuition of why that is. And so in a lot of these applied problems, I'm going to give you a logarithmic utility function because it's analytically easy to work with. And the model will collapse to something that looks an awful lot like the Solow growth model. Okay, that's how we're going to continue our discussion on, I guess, next Monday then, right? We'll probably have, I would say, 3 more classes covering the Solow model, maybe even a 4th. And then you guys will be looking at your first midterm exam. But as we get closer to it, we'll agree to a date. And it'll be on a Friday, some point probably in the afternoon. And I'll give you guys like 3 hours to take the test, okay? Don't worry about that yet. Just try to keep up with the material, keep working the review questions, and go to recitation, okay? That is it.